Along the right-hand column of the periodic table of elements is a group known as the noble gases: helium, neon, argon, krypton, xenon, and radon, also known as the rare gases. They were once called inert gases because scientists believe them incapable of reacting with other elements. Rare though they are, these gases are part of everyday life, as evidenced by the helium in balloons, the neon in science, and the half-full radon in some American homes. These gases all have similar properties under standard conditions. They are all odorless, colourless, monatomic gases with very low chemical reactivity. All noble gases are typically highly unreactive except when under particularly extreme conditions. The noble gases all have low boiling points. This is a typical property of nonmetals. You can see from the graph that helium at the top of group 0 has the lowest boiling point in that group. The boiling points then increase as you go down the graph. The density of a substance is a measure of its mass per unit. For example, a small lump of highly dense substance such as mercury or lead has a high mass. The particles in gases are spread far apart, so gases have low densities. You can see from the graph that helium at the top of group 0 has the lowest density in the group. The densities then increase as you go down the group. Radon at the bottom of this group is the densest gas known. They have their outermost shell complete and thus remain stable. They do not generally combine with other substances, nor are they affected by oxidizing agents or by reducing agents. Noble gases are placed in the 18th group on the periodic table. Since the outermost shell is complete, the valency is 0. Hence, the 18th group is also referred to as the 0 group. Helium is the most stable of the noble gases because its valence electrons are more closely and strongly held than the valence electrons in all other noble gases. This is due to its smaller atomic radii plus no electron shielding. Helium is slightly different than the other noble gas elements. It only has 2 electrons in its outer shell, so its valence electron configuration is 1s to the power of 2. Even though it only has 2 electrons, it is grouped with elements that have 8 valence electrons. The properties of the noble gases can be well explained by modern theories of atomic structure. The outer shell of valence electrons is considered to be full in noble gases, giving them little tendency to participate in chemical reactions. It has been possible to prepare only a few hundred noble gases compounds. In the case of neon, for example, both the n equals 1 and n equals 2 shells are complete, and therefore it is stable monatomic gas under ambient conditions. The noble gas atoms, as do the atoms in most other groups on the periodic table, increase steadily in atomic radius from one period to the next due to an increasing number of electrons. The size of the atom is related to several properties. For example, the ionization potential decreases with an increasing radius because the valence electrons in the larger noble gases are farther away from the nucleus and so are not held as tightly together by the atom. Noble gases have the largest ionization potential among the elements of each period. This reflects the stability of the electron configuration and points again to their relative lack of chemical reactivity. Halogens are extremely reactive elements because they need one more electron to gain a full octet of valence electrons, whereas the noble gases are extremely unstable because they already have their full octet. The octet rule states that all elements tend to react in such a way to get a filled valence shell of electrons. Anything that makes this happen is favoured, and anything that keeps this from happening is not. Halogens are reactive oxidizers, meaning they pull electrons off other things. They're typically diatomic. They may be at any of the 3 states of matter at room temperature, and they basically react with almost everything. Noble gases are well gases. They don't react with much, except under unusual circumstances.